So, we are talking about the advanced marine structure course on module 4. In the last lecture we discussed about introduction to fracture and fatigue analysis of marine structures. In this lecture we will talk about fatigue loading and fatigue analysis. The moment we talk about fatigue loading, local stresses for fatigue design need to be determined after accounting for temporal and spatial variations. It is very important that depends upon the location where you are measuring these stresses, you need to actually account for that spatial variation. I will just show you a sketch where the hotspot stresses can be varied for a welded structure. For example, in case of a welded structure, the main parameter to represent the variation in time is the stress range, because we know already that using minus rule or using a conventional analysis how to find the fatigue damage for a single stress range or a multiple stress range depending upon the summation, and we saw in the last lecture how to use the minus rule when you got multi stress range states. In this lecture we will discuss about the different methods by which you can calculate the stress range for multiple loading and then estimate the fatigue life of the marine structure. So, in case of welded structure, let us see how the spatial variation matters. This becomes my main plate of thickness T, and this becomes my attachment plate. This is my plane at which I am measuring the stresses. So, I call this as stress evaluation plane. If you look at the stress variation measured along this plane in terms of thickness of the main plate, I am trying to measure stress along this axis. Let us say this is the point where I call as knot stress. The knot stress will be maximum on the plane where I am measuring the stress evaluation. Then the stress keeps on reducing, and this is the point where we call as hot spot stress, and this is of course my fillet weld. And the reduction keeps on happening at a spatial variation of T by 2, 3T by 2 and so on. And at this place we call this as surface stress. So, this sketch refers to spatial variation of notch, hotspot and surface stresses. In a plane structure. So, what we mean to say here is, so for a welded structure the main parameter to represent the in time is the stress range. So, the basic assumptions actually made in such analysis are the following: the tensile residual stresses are always present, all stress cycles effective to drive the crack, none of them actually closes the crack, they are all effective in driving the crack. The spatial stress variation can be accounted by using hotspot stress approach. Global analysis of fatigue loading causes effects in member forces, whereas the local analysis carried out to determine the hotspot stresses. There are two kinds of analysis what we carry out for members under fatigue loading. One is the global analysis which affects the members in terms of their forces, whereas the local analysis is focused on hotspot stresses which is occurring at the stress plane evaluation as we saw in this figure. Now, if you talk about fatigue loading which can cause by dynamic loads, for example wave action, wind action, operation of machinery etc. For marine structures, of course the prime source of dynamic loading is from the waves. Now, I want to do under this fatigue loading, let us see how do I do a dynamic time domain fatigue analysis. The time domain fatigue analysis results in time series of stresses. Okay, I will call stress cycle time history. I will generate a stress spectrum, what we call as a time series of the stresses. For narrowband Gaussian process, these cycles of stresses are well defined. For more general stress time histories, cycle counting methods are effective as seen in the literature. We will talk about the cycle counting today. The time domain methods uses only the information provided by series of peaks, that is it uses only information related to local maxima and local minima. Let us say we have a jacket structure Let us look at this connection and see how the hotspot stresses are focused. Let us say this is my main member, So, let us say this is my leg of the jacket, these are all braces, and these are all nominal stresses acting on the braces. Generally the horizontal members will be subjected to compressive forces, whereas the diagonal members will be subjected to axial tension. So, these are normal stresses acting on the braces. So, this is the zone where hot spot stresses will develop. This is a zone where hot spot stresses are developed. Now, when you talk about the time history analysis or time domain fatigue analysis, the time domain actually uses only informations available to the local maxima and local minima. From the stress time history, the peaks and valleys are identified. We will take up an example and explain you. Then based on these peaks and valleys identified, effective stress ranges can also be identified, and then they are grouped using various cycle counting methods. There are various cycle counting methods available in the literature which will help you to group the stress ranges based upon the identified peaks and valleys on a given stress time history. Few common methods which are used commonly for fatigue damage analysis are the peak counting, the range counting, the level crossing counting, and the rainflow counting. The rainflow counting method is the best suitable method for fatigue damage. They are as per ASTM 1985, which is referred here below. You can also refer to Wishins and Paul's for book on random vibration theory and practice, which will help you what are the comparative advantages and disadvantages of different kinds of cycle counting methods as you see here. But in this lecture we will pick up an example to explain you how to use the rainflow counting. You can very well understand, depending upon the minor discrepancies available in identifying the cycle counting used for rainflow as recommended by ASTM, there are variations in computing the stress ranges. Let us pick up one specific case which is commonly applied to marine structures. We call this as rainflow counting method. Originally this is known as pagoda roof method. The method was first proposed by Matsushi and Endo in the year 1968. The reference available here. Now let us consider a time series of stress cycles of peaks and valleys as shown in the figure. I generally get a stress cycle like this. Let us say this is my time and this is my stress cycle. I may get a plot like this. Okay, peaks and valleys. What I am trying to do here is I am rotating this figure clockwise by 90 degrees. So, what I do is I get this time cycle going positive downwards. Okay. So, 0 will start somewhere here and will keep on going downwards. This is going to be my time. Okay. And all these peaks and valleys which are with respect to the time will now appear like this. Okay. Is it clear? Right? That is what I am trying to draw here. So, this is obviously my time and this is my stress variation. Which is sigma. For example, let us say it is in Newton per mm square. So, I have a point A, that is one point. So, I am even writing the coordinates here -2, 0, B is 1, 1, so that we can understand where we are drawing. So, these are my stress points, peaks and valleys. Let me join this. This is my stress time history. Okay. So, I get my stress time history, which I can say these are my peaks and these are my troughs because they are negative values or valleys. So, now what I do, I start from a valley and allow a raindrop to fall, simply a raindrop to fall on the roof. So, what will happen, the raindrop will roll over the roof and keep on rolling until there is a roof of projection available. So, let us try to draw this in dotted. It comes here and it stops. Similarly, the other one starts from here and stops. These are terminal points. From C again it starts, goes to D and it comes down, let us say it stops here. And at D it moves to E, then falls on this roof, then moves further and falls. So, there can be from E to F falls here, and now it moves from F and comes to this point. I call this as E dash, and from G it comes forward, ends here, and of course from H it comes to I and ends here. There are some rules which we must follow. Okay. There are some rules which we must follow before we draw the lines connecting the peaks and valleys. The time axis is drawn vertically downwards, as you see from this figure here. Then the lines connecting the peaks and valleys form series of pagoda roofs. Let us quickly see how we drew these series of lines in dotted. Each rain flow begins at the beginning of the time series and at the inside of every peak and valley. That is what we have done here. We started this dotted line from A, which is a valley, moved to B, and then it terminated there. Again from the inside of the point B, which is again starting the next line, moves to C, and so on and so forth. So each rain flow begins at the beginning of the time series and at the inside of every peak and valley. Rain flow which is initiated from a peak drops down until it reaches an opposite peak or more positive value, or it reaches a valley which is more a negative value than from a peak where it is started. For example, in this case, it is moved from D, came to E, it could see another positive value, it moves down. Okay, one can ask me a question, sir, why this has not come down and moved here? Okay, because this value is again successive peak, right. The only variation if you add this will be the stress cycle range. I will come to that later. Okay. So we have taken it here this way, and when it encounters a successive peak which is next to this, it rolls over and terminates here. That is what we are trying to say here. So the rain flow initiated from a peak drops down until it reaches an opposite peak which is more positive than from a peak from where it has started. The rain flow stops when it meets the rain flow of the roof above. That is what it is here. You can see the point E prime shows that the rain flow has stopped when it reaches the rain flow from the roof above. So it stopped here. Okay. Now the rain flow must terminate at the end of the time series. So it started at A and finished at I. The horizontal length of each rain flow is counted as half cycle with that the stretch range. We will talk about that now. Now I want to estimate actually the stress range for every half cycle. Why it is called as an half cycle? Because it had one valley and one peak. Wherever there was two valleys or two peaks, I will call this as a one full cycle. Now let us make a table. Let us say my path, cycles, stress range, let us say the path AB. Look at this figure here, AB is the path, one half cycle because one valley and one peak. I write here 0.5, one half cycle, and the stress range for this B is 1 and this is -2. So the range is 3. Similarly BC, again peak and valley, so again 0.5, and what could be the range? 4, is it not? Because B is at +1, C is at -3, so it is 4. Similarly CD, again half cycle, so the value could be 8. is it not? Then let us say starting from D it falls down and goes to G, so let us say dG. Okay, you can see here one positive and one negative peak, right. I am counting it this way, it is not coming back and going, right, it is moving from here and going, so 1 to 1. So again it is 0.5 only. And the value could be 9. Let us say EF. Now E moved from, started from the valley here, moved to the peak, and it terminated in the point where the rainflow is dropping from the roof above. So there is a full cycle completed, is it not? So I should say this as 0.5 into 2, okay, one cycle, and the value is -1 and 3, it becomes 4. And similarly GH is this value, only half cycle, so -4 and +4 becomes 8. Then HI half cycle, 4 and -2, 6. So we have got a stress range for different. Now let us make the next table saying that what is my stress range, and within that how many cycles are there. These are all different stress ranges, no, and what is the corresponding path. So let us start from so the maximum value here is 9. Let me start from 10, the stress range 10, there are no cycles, there is no path, and stress range 9, how many cycles are there, how many cycles, half cycle, so 0.5, and the path could be dG. Similarly 8, 7, 6, 5, 4, 3, 2, 1, can you fill up this? So if you look at 8, there are 2 cycles, one is 0.5 and 0.5, so I should say 1, and the paths are CD and GH. For 7 there is nothing, for 6 there is one value, that is 0.5 and that is HI, and for 5 there is nothing, and for 4 you have got 1.5 and the paths are EF comma BC, and for 3 you have got 0.5 and you have got AB, and for 2 got nothing, and for 1 you have nothing, and so on. So the stress range is what we call as Ng, so the number of cycles. This is sigma g, stress range of the group, and cycles is Ng. Now we can find damage for each group. Now damage for each group dG is known to be Ng by Ng. Ng is known to me because from this table I know, but capital Ng is equal to A Sg of minus m, is it not? A of course is a constant and m is the slope of the Sn curve. Now, if you know corresponding Sn curve based on which this experiment was conducted and material was derived, that Sn curve will use and find the slope. Usually it is 3 for standard materials used in marine structures, and Sg you already know for various groups. So, you will try to find dg, that is d1, group 1, group 2, group 3, etc., and then if you really want to find the cumulative damage, add all of them, and this value is exceeding 1 or at least equal to 1, one can say the damage has occurred. Okay. This is one of the easy methods by which one can find out the fatigue damage. This is what we call as rain flow counting method. Okay. Now, we already seen couple of more methods which can also be used for finding out fatigue damage similarly. Now, based on fatigue damage estimates made from different methods, it is seen that the damage what you have made using rain flow counting is lesser than that of the damage what you have made using RFC, is lesser than the damage estimated from LCC, is lesser than the damage estimated from PC, and the damage estimated from LCC is as same as the damage estimated from NB. I will talk about all these things. RC, it is range counting, this is rain flow counting, RFC, and LCC, level crossing counting, NB refers to narrow band approximation. We are going to talk about this in the next lecture. PC, peak counting. So, rain flow counting gives you a conservative estimate compared to that of the range counting, but it is giving you an estimate of damage based on fatigue lower than the level crossing counting and the narrow band counting, right. So, there is an improvement available on the time series estimates of fatigue damage which is based upon the rain flow counting method, but this is not a method suggested by the local engineers or engineering group, it is suggested by AST. So, it is an important technical method by which fatigue damage can be assessed if the stress cycle time history is available to you. Okay. So, if the time history is available, just turn the curve, make the axis of the time downwards positive, you get the stress range of peaks and valleys distributed to the right and left of a vertical line, identify the stress cycles, the stress ranges, group them, and if you know the corresponding Sn curve, then use this equation and find the damage on each group. If you really want to find the cumulative damage using minus rule, you can apply this and say that of the entire group can be simply G equal to 1 to Ng as number of group, dg equal to, if this sets to 1, then the damage has occurred. This as per the minus rule which we saw in the last lecture. Thank you.